All right, guys, so we're going to do one more partial fractions example. This time, we're going to do one that first has substitution that then results in a partial fractions. So this is substitution, then partial fractions. So what I notice about this particular question is that there are e to the x's everywhere. And so just a tip, a good idea when you see the same type of function everywhere, a lot of times letting that function be your u will turn it into a problem that looks more familiar, that looks more like the type of problem that you're used to seeing. So because there are e to the x's everywhere, I'm going to start by letting u equal to e to the x. So then du is equal to e to the x dx. So I have two options here. I can multiply by e to the x over e to the x to get my factor of e to the x. But what seems more straightforward to me and will probably make for a little bit more of an efficient way of approaching the problem is noticing that there's a factor of e to the x in the numerator. So like I can't just take this because that e to the x right there is not a factor. It's like plus 4 to e to the x. Instead, I can actually factor out an e to the x here. So I have 2 e to the 2x minus e to the x plus 4 over e to the 3x plus 4 e to the x. There's really no need to factor it out in the denominator. The only reason that I'm factoring it out is so that I can clearly have my du here. So this is my du. And now every e to the x is going to get replaced with u. So I have 2u squared minus u plus 4 over u cubed plus 4u du. So in this case, first I would normally want to start by thinking about a substitution. Derivative of the denominator is 3u squared plus 4. Clearly that doesn't do the trick. So then I notice the form of the problem. It is a rational function, and the degree of the numerator is 2, and the degree of the denominator is 3. So for my first step here, no division is necessary. So no division necessary. And then for my second step here, I want to factor my denominator. So I get u cubed plus 4u. I notice that there's a common factor of u. So I factor that out and I have a u squared plus 4 left. Note that that is a sum of squares. We know a difference of squares. Difference of squares is like x squared minus a squared, and that factors to be x minus a times x plus a. Unfortunately, a sum of squares cannot be factored. So sum of squares, that's x squared plus a squared, cannot be factored. So in this case, that means we are done. And what I notice here is that we have that quadratic polynomial, that irreducible quadratic polynomial that could not be factored, which tells me at this point, I notice that this is going to be a case 3. It has the irreducible quadratic polynomial, but it only occurs one time. So this brings us to our third step. We create our partial fractions decomposition. So here we'll have that 2u squared minus u plus 4 over u times u squared plus 4 is equal to a over u. And I'm going to use my initials this time. Why not? So u squared plus 4 is quadratic, power of 2, which means I need to have a power of 1 on top. It's u, not x, so I will have eu plus b. There we go. So then in my step 4, I multiply both sides by that original denominator, u times u squared plus 4. And what I end up with is 2u squared minus u plus 4 is equal to a. The u's cancel out, u squared plus 4, plus eu plus b. The u squared plus 4 cancels out, and I have times u. And now I'm actually going to still stick to method 1. We won't see method 2 until next class, so like after March break. So I want to stick to method 1 here. Method 1. And my zeros, the only zero I have here is rather u equals to 0. Now this is because u squared plus 4 can't factor. There is no value I could plug in to make that equal 0. So I know I've got 3 unknowns here, but only one 0, that being u equals 0. So we'll start off by plugging in that u equals 0. And what I get is 0 minus 0 plus 4 is equal to a times 0 plus 4 plus e times 0. Well, actually, all of this is just going to go to 0 because we're being multiplied by 0 at the end. So then I get 4a is equal to 4, and a is equal to 1. Okay, so now I'm done with my zeros, which means that I can rewrite this thing with the a of 1 that I got. So I got 2u squared minus u plus 4 is equal to u squared plus 4 plus eu plus b times u. So now I'm sticking to method 1. I'm going to pick other values to plug in. Well, I haven't plugged in 1 yet, so I'm going to go with that. So we'll have u is equal to 1. And I get 2 minus 1 plus 4 is equal to 1 plus 4 plus e plus b times 1, which gives me that e plus b is equal to 2 minus 1, that's 1 plus 4, that's 5, minus 1 minus 4. So this tells me that e plus b is equal to 0. And notice that we didn't actually solve for one of them. That's okay. We're going to say I had 2 things left over, so I knew I was going to have to plug in 2 values. I'm going to plug in my second u value now. So here I get u is equal to -1. It really doesn't matter. I'm picking these values just totally randomly. You could pick a different value if you thought that that would be easier to plug in. So here I'm going to get 2 plus 1 plus 4 is equal to 1 plus 4 plus negative e plus b times -1. So this gives me 7 is equal to 5 plus e minus b. So e minus b is equal to 2. So what I have now is a system of equations with both of these values. So I have the e plus b equals 0 and the e minus b equals 2. And so this would happen regardless of whether or not we were doing method 1 or the other method 2 that we haven't learned yet. So we need to solve this system of equations. Need to solve system of equations. Well, don't worry, this is actually not that hard to solve. So I'm going to do e plus b is equal to 0, and then e minus b is equal to 2. So this is my system of equations. So we really have 2 options here. I could solve for e. I could say that e is equal to -b, and then plug that into the other equation. Or another thing I could do is find a way to add them together to cancel a thing out. So in this case, I don't have to multiply by anything. I already have minus b. So I'm just going to add these 2 equations together. So I'll get 2e plus 0b is equal to 2. So in other words, 2e is equal to 2, which gives me that e is equal to 1. There we go. And then I can plug it back in up here. So plug back in to find my b. So in other words, I'll have 1 plus b is equal to 0, which gives me b is equal to -1. So we've solved our system of equations, which allowed us to solve for e and b. Now, again, like I said, another way that I could have done this, we'll just do this on the side. It's up to you and what you're more comfortable with, and really what the equations give. So I could have said e plus b is equal to 0, which means that e is equal to -b. So then in my other equation, I would replace e with -b, minus b is equal to 2, and get minus 2b is equal to 2, which would give me the same b equals -1. So replace e with -b, solve for one variable in terms of the other. So either of these methods is good. In this particular case, that second method was really straightforward because one of our equations had it equal to 0. But the first method was also really straightforward because I already had a plus b in one and a minus b in the other, which means they just canceled out without having to multiply by anything. Okay, so now this brings us to our step 5. We are almost done with this problem. In our step 5, we rewrite the integral. So I'm going to get the integral of a, which is 1, and a was over u, plus eu plus b, so that's u minus 1, over u squared plus 4 du. Now this first one is really simple. This is a known form. This second thing is something that shows up at the end of partial fractions pretty regularly. I'm just going to rewrite this so it's a little bit prettier. So I have 1 over u du plus the integral of u minus 1 over u squared plus 4 du. Now what I notice is this u squared plus 4 looks a lot like arctan. And remember, we've said when that's the case, you can use it to simplify, or rather to separate the numerator. So I'm going to end up with here 1 over u du plus the integral of u over u squared plus 4 du minus the integral of 1 over u squared plus 4 du. And notice this is a known form. Known form. This is a known form. And this is just a simple, really quick substitution. W is equal to u squared plus 4. dw is equal to 2u du. So I just multiply by 2, divide by 2 to get 1/2 the integral of 1 over w dw. So I have 1/2 ln of the absolute value of w plus c. So I get ln of u plus 1/2 ln of u squared plus 4 plus arctan of u plus c, and then u is equal to e to the x. So ln of e to the x, 1/2 ln of e to the 2x plus 4 plus arctan of e to the x plus a constant. Now there is one last quick thing we need to do here. Ln of e to the x, remember ln and e are inverse functions. They cancel each other out, so this just equals 2x. So our final answer is x plus 1/2 ln of e to the 2x plus 4 plus arctan of e to the x. By plus, I mean minus. Love those minuses. So minus arctan of e to the x plus a constant. And then we don't want to forget, actually, I was forgetting it, my bad, that, that our a in that u squared plus 4 is 2, and arctan does take a 1 over a. So we're going to need to make sure that we remember to multiply that arctan by 1/2. So that's like my 1 over a. So we have the 1/2 there, and then this is our final answer here. So sorry that I had like screwed that little part up for a second there. Okay, so we have minus 1/2 arctan of e to the x over 2. Wow, I just really screwed that up. So this is arctan of u over 2, e to the x over 2, e to the x over 2. Sorry, I was treating that 4 as if it was a 1. Okay, so there we go. Final answer. All right, bye guys.